Today I'm going to talk about two extensions of the Kalman filter, the uncertain Kalman filter and the information filter. And as the first thing to try to understand is, we talked about the Kalman filter next week, and we said that you need linear models. And what the extended Kalman filter does, what we've seen last week, is that it expands the nonlinear functions, so it can be observation model or motion model, and tries to fit a linear approximation locally on the previous mean. The idea is to find a better way to have a linearization that consider something a bit far away from the mean and tries to capture the nature of the function in a better way. And this is what the ascendant transform does. And if we then apply the ascendant transform instead of the Taylor expansion to the Kalman filter, we obtain what's called the ascendant Kalman filter. If you look at graphically, we have here our initial distribution. So we have our mean, we have our covariance, and we now apply a nonlinear function, and we end in a new mean and a new covariance. So the way the AKF does it is it considers this point, it's propagating the point through the function, finds a linear approximation of the function, so the tangent line, and then it does a linear error propagation of the covariance there. And these are the formulas we've seen last week, where you do the Jacobians times the covariance matrix times the Jacobian transpose. The way the ascendant Kalman filter works instead is that it's not considering only the mean, but it's considering a set of points which are within this distribution, and they kind of represent the shape of the covariance matrix originally. These points are called sigma points, and we'll see later on how you can compute them. But for now, just imagine that you get some points in this space. Then it propagates all of these points through the nonlinear function, and it obtains a set of other points, which are the transform points through the function, and then it computes the statistics of this point. So it computes the new mean and it computes the new covariance matrix, but just considering how these points actually influence the mean and how these points influence the covariance matrix. How does it work? So the idea here is that you want to follow these steps. You need to know how to compute the sigma points. You need to associate a weight to each of these sigma points that is used to reconstruct the successive, so the new mean and the new covariance. You then transform the points through the nonlinear function, and you compute the new mean and the new covariance as a weighted sum of the sigma points. So you don't need to do any linearization around the mean, and you also do not need to know any gradient of your function. So you might use any function, and you can just apply these steps to that, and you get a propagation of the uncertainty and the mean over that. Okay? So how do we actually compute the sigma points, and how do we compute the weights? Do you have any idea? Any suggestion? I mean, we have seen before, we have here our mean and our covariance, and we want to transform this. What could be like a way of getting the sigma points? What could be some, potential points that you want to take? Yes?
Just sample from it?
Yeah, we could sample, and we will end up with a set of points here. That could be a viable way. But then how many points do you get? And how can you be sure that you get enough points for doing what you want to do? So one way is, if you imagine that this is an ellipse, and you want to parameterize an ellipse, you basically have the axis of the ellipse, and you take, this is one axis, this is the other axis, and then you might take a point here, a point here, a point here, and a point here, no? And then you kind of get your parameters back on the other parts. That's somehow one pictorial way of seeing this. But then the problem is, how do we set the weights? Because these are just points, and you want to be sure that those points actually have a meaning. And also, when you do the weighted mean and when you get the weighted covariance, they also need to have a meaningful idea. So we only knew one thing, is that what happens before I apply the function, right? So ideally, we want to know that, want to be able that these points are able to represent well the initial distribution, right? And that's exactly how you can imagine them. So you select a set of points and a set of weights, such that the weights sum up to 1, so you don't want to have any strange expansion. You just want to say it's a combination of weights, and I know that all of them must sum up to 1. So it's what's called the convex combination. And then you want to be sure that when you take the weighted mean, so when you take the sample mean in this case, so the sigma points will be your samples, with the weights that you put there, you end up with the mean that you have in your original distribution. And the same thing if you get the sample covariance, where it's just a weighted sum of the sample minus the mean times the samples minus the mean transpose. This is what's called a rank 1 matrix, because you have a vector multiplied by the vector transpose. So, and it's different than when you do this, if you have a vector x and you do x transpose x, this gives you one number. And if you do x transpose, this gives you one matrix. Okay? And so it's not a mistake that the transpose is up there. And exactly, when you get the empirical covariance, you want to make sure that the empirical covariance is equal to the original covariance matrix. Okay? So basically, this defines a set of constraints that you want to put on the sigma points and on the weights. And you should, in principle, if you're able to solve this kind of systems, you get a set of sigma points and you get a set of weights that you can use for the ascendant transform. There is also not a unique solution for this. This is an under-constrained problem. So there are some ways of getting this solution in a smart way, or somehow understanding a bit the structure of your problem. So one way is that for the sigma points is the first one you take is the mean, because I mean the mean characterizes a lot your distribution. You want to propagate it over. And then you take points which, as I said before, somehow they lie on the axis of your matrix. Okay? What it says here is you take the ith point when ei is from 1 to n as the mean plus this thing here. This is the square root of the covariance matrix multiplied by some number, and we'll see now what this number means. The reason why there is something multiplying the covariance matrix is coming from the fact that you want to reconstruct then your original covariance matrix. So if you don't put n here, which is the dimension, you will be not able to reconstruct it correctly, because it will be smaller. So you need to account for the size of your space. And what the square root does is gives you somehow, each vector of the square root of a matrix gives you one of these directions. They might be rotated, but in principle it gives you a set of potential directions of this ellipse. And when you take the one with the plus, you're going in one direction. And when you take the one with the minus here, you're actually getting the symmetric on the other direction. Okay? Any question on that?
So
yes?
this dimensionality means the torturing of the eclipse, right?
It means number of dimensions. So if you have 1D, 2D, 3D, so the covariance matrix like n by n, and this is the n that you're considering there.
And the scaling parameter only refers to the size of the matrix of the eclipse. Does it also refers to the maybe the rotation of the eclipse?
No, this is just all the rotation is in here. This just gives you, and so in principle, so these things get coupled with the weights. Okay, so this tells you how far you want to go on this line. Okay, and then you couple it with the weights and gives you normalizes everything together to recover the covariance matrix. And the n is there because you want to be sure to be, when you are in high dimension, there is some problems of distances, so you want to be sure you're far away, so enough far away from your center, okay? But in principle, this is just a way of deciding how far you want to have the points, okay? There is an offset, which is n, and then there is lambda, which is a parameter that you can play how far you want to go in these directions, okay? Any question?
So again, this annotation is the E column vector of my covariance matrix.
Exactly. So this tells there's a covariance matrix. You multiply by a scalar, okay, and then you take the square root. This gives you another matrix, and then you take the eth column of this matrix, okay. And here it's I minus n because you need to. You don't have more than n, and you have 2n sigma points. No? So the number of sigma points is normally 2 times the dimension plus 1, because you take the mean, and then for each dimension, you take the couple of symmetric points. Okay? Any further question? Okay. So, do you know how to get the square root of a matrix? Or what is a square root of a matrix? Any idea? I mean, what is a square root of a number? So if I have a number, no? Let's say a squared. This is equal to a times a, right? Okay. So if I want to take the square root of a squared, this is equal to a, right? So
only if a is equal greater than 0.
yeah, okay. I mean, let's not go too much into the complex number part. But let's say, or you can do it differently. Now you can say that a is equal to square root of a times square root of a, right? Okay? So basically, the square root of a number is another number that multiplied by itself is equal to the first number, okay? And you can do the same with a matrix, no? You can say, I have a matrix A, and I can say that square root of A times square root of A. No? I mean, I'm just defining the square root in a way. So, and that's exactly how we do with matrices. So the square root S is defined such that the original matrix is equal to the sum of S per itself. Okay? That's actually one way of defining it. We'll see later on there's also another way of defining it. So how can we compute it? We can compute it by considering the eigenvalue decomposition of the matrix. Okay? What's also called diagonalization. How many of you does not know what's an eigenvalue decomposition? Okay, good. So in principle, we have now sigma, and we have V, which is the matrix, orthogonal matrix that spans the space defined by sigma, multiplied by diagonal matrix, and multiplied again by the inverse of V. Okay? And V is orthogonal matrix, so you can also put the transpose, which is the same operation. We can write it in this way. So we have V, we have a diagonal matrix. We can take a square root of a diagonal matrix easily. We can just take the square root of the elements of the diagonal. And now we have a nice decomposition of sigma, which has a part here, which is V something. Okay? And then here we have again this something with V. Okay? Now, if we go and write it in extension, so we can define that our matrix is just S, V, the square root of my diagonal matrix, times V minus 1. Okay? So if we now show by, this is done by construction, so you can just now expand the product of S with itself, we will see that this is equal to V times D square root times V minus 1 times, again, the same one. Now we have V minus 1 times V. They simplify itself, so it gets an identity matrix. And we get the diagonal squared, square root of the diagonal times the square root of the diagonal. It gets to the diagonal matrix again. So we then have V, D, V minus 1, which is exactly how we define sigma before. Okay? So basically, what does this do? This basically is telling you, you take the eigenvectors of your covariance matrix, which are the axis of the ellipse, and you just have this scaling for each axis. So one column of this will be the first axis times one element of the times the square root of one of the eigenvalues. So it's really like the direction of the axis, and as a distance in this case you have the square root of the eigenvalue. So it's really like the point on the ellipse which has size 1 in terms of the way you define the ellipse as a geometric figure. Okay? There is also, this is expensive. It takes it's n cubed, but it's also not very numerically stable. So there is another way of computing the square root of a matrix, which involves what's called the Cholesky decomposition. Does any of you know what the Cholesky decomposition is? Okay. So the Cholesky decomposition is an operation that takes a matrix and decomposes it in the product of two matrices, which are lower triangular, which means it's a matrix that it's made in this way. It has all zeros here on the upper triangular part. Then it has some numbers on the diagonal and also some numbers down here. Okay? So it's always 0 on the top part, and it's always non-zero on the bottom part and the diagonal. And when you, it has some specific properties, like you can get easily the determinant of this by just multiplying the values of the diagonal, and it's used for a lot of other things. But you can use it for computing the square root of the matrix by just twisting a bit the definition of the square root, where instead of saying that the square root is of sigma is done in a way, let's say, S times S, now it becomes something like S times S transpose. Okay? So you can just change a bit the definition of a square root. It will still match the definition of a square root of a number, because the transpose of a number is the number itself, and will still be useful for defining sigma points. The difference with the previous definition is that we do not have sigma points on the axis of the ellipse any longer. They might be arbitrarily inside, but they will still span the whole space in different dimensions. Okay? So if you want to see it visually, will be something more, before we had this nice ellipse, we take the SVD, or like we take the eigen decomposition, and we end up with sigma points on the axis. So this is the mean, and then we get some sigma points here. And if we instead use the Cholesky, and now I'm not sure what will end up, but I will just try to make my best, you might get something like this, and maybe this one. No? So you will get some sigma points which are somehow in this way. No? So you don't necessarily have the axis of the ellipse, but you will span the whole space anyway. Okay? And they will be roughly on the same iso distance, iso surface from the mean. Yes?
But those axes are not orthogonal anymore.
Yeah, that's true. That's true. They're not orthogonal, but they're still independent.
Okay.
So the important thing is not that they are orthogonal, but that they are linear independent, so that you can reproduce the same dimensionality of the space there. You're not doing any projections anywhere. Okay? So if they are too much parallel, you will have problems, but I mean, this is probably not exactly how the axis will be, because if you look at the structure, you still get the vectors, and you still see that they are zeros there. So there is no way that two vectors will span and will be exactly parallel. No? So we still can keep a lot of the properties of the square root with the eigenvectors. So that's just to say that you don't have to take orthogonal eigenvectors or orthogonal columns for the sigma points, but they have to be linearly independent. Okay? And that's actually what is mostly used for the UKF, because it's very quick and fast to compute, especially if you have sparse covariance matrices. In case you don't have, it's anyway faster than an eigenvalue decomposition, and it's also more numerically stable. Okay? It means that if one of the eigenvalues of your matrix is close to 0, it's not a big problem for the Cholesky decomposition, but might be a big problem for an eigenvalue decomposition. Okay? That eigenvalue close to 0, it means that your distribution is kind of squeezed on one dimension. So it's really like flat on one dimension instead of being quite fat and large. Okay? That's the idea of the eigenvalues. And again, another property is that both L, that sigma, they still share the same eigenvector. So if you do an eigenvalue decomposition of L, you will still get the same eigenvectors that you will get for sigma. Okay? And another thing that you need to be considered for Cholesky, we'll see later on also in the class, is that this matrix must be symmetric and positive definite. Otherwise, you cannot compute a Cholesky decomposition. But in the case of a covariance matrix, that's also the same definition of a covariance matrix, which must be symmetric and positive definite. Okay? Yes?
Can you give us a simple example of how to calculate and make a square root of, like, for example, 2 by 2 matrix?
I mean, that will take a bit of time to compute the eigenvalue decomposition of Cholesky, but it's really doesn't, I mean, it's not gonna, you can, this function here, Cholesky and eigenvalues, they are implemented in any numerical tool. So you can just call the function which is eigen decomposition or Cholesky, and you will get your matrix quickly. So I'm not going to do any linear algebra tutorial right now, but that's really, you can Google Cholesky or eigenvalue or square root, you will find examples there. Okay? So if, exactly, so that's the idea I was saying before, that the sigma points do not have to lie on the axis. They can, but it's not necessary that they do it. And it's just a set of points, and they are kind of symmetric. And the way that they are aligned or put in this covariance will just be then used for the computation finally, and the weights will account for where they are. Once you compute the sigma points, you can see an example, for instance. These are a set of potential sigma points, and in green you see the square root. I think this is the Cholesky square root, and still plotted as a 2D covariance, 2D ellipse. And here is your original matrix. So as you can see, it's not, so then it's not aligned on the same, it's not completely aligned. So the sigma points are not on the axis of the original ellipse, but it's still fine for our purposes. Okay? Now, how do we compute the weights? Once you select the sigma points, the weights comes naturally from the fact that you want to reproduce your original mean and your original covariance. So we set, and this is the way we set them for what's called the scaled sentence transform, which is a twist on the original one, but for what it matters you, that's how it's mostly implemented, the Ansenden Kalman filter. The only thing you need to take care is that for the mean, you have different weights according if you're using it for computing the mean or if you're using it for computing the covariance. Okay? And that comes from the way this whole Ansenden transform is structured. If you get the mean, you just get the lambda, which is the parameter that decides you how to go away from the mean, divided by n plus lambda. And for the covariance, you need to add these terms here. I don't want to go too much into the details, but these terms here accounts for effects which are on higher order statistics of your distribution. So I guess like mean and covariance is clear for you, but there are some other statistics of higher order, which are the skewness that tells you how symmetric a distribution is, and the kurtosis that tells you how fat the distribution is towards points far away of the mean. And these two terms actually account for what's called excess kurtosis. If you remove them, you basically take the weights for the covariance as the same as the weight for the mean, you will not consider these higher order terms, and you will end up in just considering the first two moments. But that's how the filter is defined. And then all the other weights for the mean and the covariance are the same for all the other sigma points. And they are just 1 over 2n plus lambda. Okay? So this, again, is for computing the means. Then you get this 2 for computing the covariance. And there are a set of 3 parameters here. There are some common values for the parameters, like for instance, if you're using a covariance matrix, beta is normally set to 2, and that's been found empirically, which in a way that they give the best performance for different class of families, okay? For different families of distributions. Now, how we can recover the covariance then again? It's by projecting or transforming each sigma points according to our function g, and then computed the mean, the weighted or the empirical mean from the sigma points with the weights we computed so far. And the same is for the covariance. We take the mean we computed, we put it here, we take the difference, so the scatter between the sigma points transformed by the function minus the computed mean times the same thing transpose, and weight it up according to the weights that we computed before. Okay? So that's the essence of the uncertain transform for propagating uncertainty over nonlinear functions. And it just boils down to computing the sigma points, computing the weights, transforming the sigma points, and then recovering mean and recovering covariance. Mm-hmm.
So, yes, what's the meaning of G?
G is the function. G is the nonlinear function that we are using. So this whole idea is to how to propagate first and second order statistics of a random variable through a nonlinear function. Okay? And G is our nonlinear function. Okay? So before we just introduced them in a way of reconstructing the same statistics of the random variable before applying the function. Okay? And now it's what happens when we actually have to propagate through the function. And if you remember this plot from last week, where we were analyzing how a normal random variable, a Gaussian random variable, behaves when transformed through nonlinear functions, you see that there is this kind of strange behavior of the distribution. And if you compute now the mean and the covariance of the resulting function, you get this solid shape here. And if you use the uncertain common filter, then you will get this dashed line, and this will be the mean. So you get something which is very close to the original distribution. Okay? So here again are a few examples. So if we just have a very easy linear function, which is just a translation, you can see that the shape of the covariance doesn't change. So you can still use an uncertain transformation to propagate uncertainty through linear functions, and you get what you will expect, that the shape is the same and only the mean is moved because you have this function here. But if you get now a nonlinear function that squeezes everything together, you can see how this initial random variable with the sigma points then gets transformed to something like this, and you get a nice squeezed distribution there. Okay? So this is a summary slide. I'm not going to go through, but it's good for you. So you just have one slide where it says everything of what you need to do. That's how you compute the sigma points. That's how you compute the weights. And these are the parameters I was telling you before. So this, okay, there's a typo. This you don't see it here, but actually appears in the way you define lambda. So lambda is defined in terms of these values. I know it's getting a bit tricky, but imagine like to use this as a cookbook. This lambda is something that has to be in this form to be able to recover the mean. And then you have these additional parameters, which is the real parameter, you should think about it. And that tells you how far these points are from the mean. Okay? This together, they play the same role. This has an influence, as you can see here. And you can play with them and just decide where to put them. So it's really, it depends on the function you are considering. And some functions, or depends also the amount of uncertainty. So you would like to have, you need to know if you want to have more far away information from your function, or you more close by information. And the more linear the function is, close by, it's actually nice. The more nonlinear, the more close by points you get, the more nonlinearities you capture. I'll show you what it means in an example later on. And then you have beta, which is fixed to 2 if we use Gaussians. And these are the parameters. So basically the only free choice you have is around these two parameters that. You can also change beta, but it's just a very good parameter value if you're using Gaussian distributions. So here you can see some example on how these values modifies the distance of the sigma points. So if you have alpha very low, and so if you keep k to a fixed value, let's say 3, and you play with alpha, the bigger you have alpha, the more these points are spread around the mean. And if you instead keep alpha fixed and you move k, the bigger you have kappa, the let's say also the further away these points get to the mean. Okay, the difference is alpha influences also some higher order statistics, because if you remember before, was in the weight, was also in the weight for the mean in the covariance computation, while kappa only influences the distance of the points and influences in the same way mean and covariance. There are free parameters. There is no rule on how to choose them. Okay, I'll put a slide first before, because there is a nice example. I want to do it later on, but this probably it's the right time. So imagine that you have a distribution like this when you use angles. You remember it from the initial discussion on the models. This is a motion model which is nonlinear, and according to how much noise you have in your angle, you get something like close to a banana shape. This is the AKF approximation, so it only considers the mean here. And this is what you will get with the uncertain Kalman filter approximation. So you start to capture part of the uncertainty here and there. So this Gaussian gets bigger on down there. And the further away you have your sigma points, the more you will capture this part here, so these tails. So this will get larger and larger, and also larger in that direction. And the closer you have the sigma points to your mean, the closer you will get to something close to an AKF approximation. Okay? So that's somehow the idea on how these parameters will influence for real your distributions, your resulting distribution. So if we get back now to how to use the uncertain transform for filtering, we can get back to the Kalman filter and the extended Kalman filter. So we know that we have this part here, which is the prediction step, where we propagate our statistics through the first order approximation. We propagate the mean through the function. We propagate the covariance through the first order propagation of the uncertainty. Then we have, when you get an observation, we propagate the uncertainty through the Jacobian of the observation function. And in this way, we compute the cross correlation between the observation and the state by multiplying these two guys here. And this is again the Jacobian. Then we compute the error by considering the real observation minus the expected observation through the function. And then we update everything. Now, what do you think we should modify for the UKF? So we need to modify the way we compute the mean, the way we compute the covariance, of course. We need to modify the way we compute also this mean, right? This is again a mean projecting the observation. We need to modify a way to compute this covariance, okay? And we also need to find a way of modifying this part here and this part here. Because basically every time we have a Jacobian in the extended Kalman filter, we need to use the ascendant transformation because we are not considering the Jacobian any longer, okay? For the prediction step is actually quite straightforward. You just replace the mean by the mean computed by the sigma points propagation, and you can replace the covariance as well by the covariance computed using the sigma point weighted sum. So here you apply directly the ascendant transformation. It's slightly different when we do the prediction. So not the prediction, the update. So these are the formulas for the prediction. These are the sigma points. These are our nonlinear functions, so the transformed sigma points. We compute the new mean. We compute the new covariance. And of course, we add the covariance of the motion model. So we add the error that we have in our motion. When we do the correction step, we still need to use the sigma point propagation for the observation, but there is a slight twist for doing the things correctly. So the first thing to consider is we take again the sigma points of the predicted state, and in principle we don't have to compute them again because they will be the same one that we can get before, just the transformed one, right? Now we have the transformed sigma points considering our h function. We compute our mean, we compute our covariance, and up to here is what we've seen so far, okay? So that's what we've seen. This is the covariance of the observation. We add again Q because that's observation noise. What is the twist here is this part here, because we also need to compute the cross correlation, and we can use the ascendant transform for this as well, but just considering what is the definition of a cross correlation terms. And this is the empirical cross correlation. So you get the first variable minus the mean of the first variable times the second variable minus the mean of the second variable transpose. No? That's basically how you compute. It's a definition of cross correlation. Okay? And we need to use the sigma transform, the ascendant transform also for this one. Okay? Because before we had this multiplication here, which is the cross correlation, and we are not using the Jacobian any longer. So we also need to transform this part here through the ascendant transformation. That's what we get here. And then finally, our Kalman gain is the cross correlation part computed here, and our inverse innovation covariance, which is what we computed here. That's S inverse. Okay? And here we have all the components to get the Kalman gain, and then we apply roughly the same formula. It's just a different way of computing these terms. The terms that we had here in the Kalman gain is now computed directly with the ascendant transform, and these terms here is also computed directly from the ascendant transform. Okay? Any question on that? Okay. Finally, we need to then apply the Kalman gain to correct the mean, and we just take the predicted observation minus the measured one times Kalman gain. That nothing is changing there. Something is slightly changed when we update the covariance matrix, because in the original Kalman filter here we still had a Jacobian of the observation, which now disappears. And we can just do some here in the next slide, some simple linear algebra tricks to actually get it in a new form where we do not need the Jacobian any longer. So this was the original form, Kalman gain, Jacobian times covariance. We can now expand everything. We can replace this term by what we actually computed already, by transpose. That's the cross correlation term. So in principle, we can just apply this, but if you go on and you look at the structure, you can again multiply and divide by S. You end up in the structure here. So this is just the same. You end up down here, but just putting the transpose inside. And you see that you can, since this metric is symmetric, you can remove the transpose with this matrix. And this is another way of also seeing the update rule for the covariance of the Kalman filter. This also has a very nice interpretation in terms of what's happening to the information flow. Here is basically saying this is the original covariance matrix before, so that's the amount of uncertainty I had before. And to this uncertainty, I actually subtract the information that I get from my observation, that's the meaning of S, and multiplied by the gain. So the Kalman gain somehow is the optimal projection of the information of on your observation space to your state space, okay? So it's like how much of this information I have to bring up. You can imagine it in this way. And that's another way of interpreting the update rule of the Kalman filter. Does it make sense? So, I mean, whenever you have covariance metrics or matrices that actually weight the space in different ways, whenever you need to transform them or put up, you always have this kind of sandwich rules that it's a way of keeping the symmetry of your matrix intact. And it always means that you're transforming, projecting, or doing a change on this matrix here. And what here means informally is that you are taking this information and projecting up to your original space in an optimal way, because the Kalman gain has been proven for linear case to be the optimal gain for that. Okay?
I have a small question regarding the transition of the third row to the fourth.
This one?
Yes. How is this transition?
Oh, that's a usual trick. It's basically, I mean, I can write it here, it's easy. You basically have in there sigma xz times identity, right? You know that you take a matrix, and you multiply by its inverse, and this is equal to identity. Okay. And you just say, I remove this, I put this. Okay. It's like when you do, I multiply by A divided by A. These are the usual tricks that you do.
Yes, the one page, this is ST, the same as ST in line 9, in page 32. Yes.
Yeah, that's exactly the same one.
And why is it necessary that S inverse times S equals identity matrix?
That's just the definition of the inverse. The inverse of a matrix is that multiplied by itself gets the identity. Okay? Good. So, and we just put S there because we wanted to end up in this form. So we could have put any matrix, but we wouldn't get anywhere with that. Okay? So if you now have a look at the differences between the UKF here and the AKF here, you will see that when we project this random variable through this nonlinear function, so that's the same plot as before, but now in comparison with the AKF, we will get a better approximation of the UKF to the true first two moments of the distribution. So the black again is the true one by really considering the moment of this strange distribution. The shadow here, the dashed, is what we get from the UKF, and here instead is what we get from the AKF. So you can see that the mean has been moved away of this distribution, and the covariance is actually not reflecting the real covariance. In this case, it's a 2D, so the variance of this true. And this just shows you that when you have a nonlinear function, it's important to consider things which are far away, also, I mean, things which are not at the mean, but also considering some other second order or third order properties of your function, so that you get a better approximation in there. Okay, so that's the whole gist of it. If you have small covariances, you don't see too much of a difference. I mean, that's what we have seen also before. The AKF is pretty good in approximating your random variable if you have low uncertainties. And that's because you're actually only considering parts close to the mean which are important. Here it's very narrow distribution, so the part of this function that actually influences the mass of the distribution is local, close to the mean. And if you project the two, you get still better results with the UKF, but also the extended Kalman filter is not too bad in approximating that. Then here is the same example I've shown you before. Can quickly skip this. And if you now see it, the full spectrum, and we see what happens with the samples and everything, you can see that this is my original distribution, and in blue are the samples. I apply now this function f, and when I get down, you get this new sample set, so there is a very nonlinear function, and my mean and covariance, they change in this way. Now, if you considering the linearized filter, so the extended Kalman filter, the only thing that we consider is the information at this point, which is the mean. We propagate it down there using the linear propagation, and we end up with this as my new mean, and this as my new covariance, which is far away of what we actually want. And if you use the ascending transform, you compute the sigma points in this way, you propagate all of them, you do all computation for getting mean and covariance, and we end up with the green covariance matrix and the green mean, which is much closer to the real mean and the real covariance. Okay? So, in summary, and then we can have a short break, the ascending transform is actually an alternative to linearization, to Taylor expansion, extended Kalman filter, especially if you have to deal with higher uncertainties and high nonlinear functions. There is another properties, which is you don't even need to have to compute the gradients of your function, because everything is done through function, to applying the function to the sigma points. In some way, you can see it's getting closer to non-parametric methods like particle filters, where you have a lot of samples and you move all the samples. And in this case, there's still a bit of determinism inside. There's still the assumption that the underlying distribution is, can be well parameterized by a mean and covariance. But it goes more into the direction of sampling rather than in the direction of closed form computation of your statistics. There are some free parameters, and we have seen how to set some of them, how some of them relates to each other, but there is a kind of a degree of freedom in choosing them that depends on the application. And we also show how you can implement a Kalman filter, a version of the Kalman filter with ascending transform, and how all the single steps plays together and the full algorithm for that. So there is some, let's say, good and bad of both. If you have linear models, they perform the same. There is no real difference. They both are able to correctly approximate, I mean, not approximate, but correctly compute the moments for linear functions. For nonlinear models, the UKF is better than the EKF. In the general case, there is not much of a difference. So the nominal case is not so much of uncertainty and not so nonlinear function, so you don't see much of a difference. But the advantages of the UKF is if you have a very cheap sensor, it might be useful to use it because the uncertainty grows and you might have overconfident result. Another plus is that you don't need to compute Jacobians. So in case your measurement function or your motion model is not, you cannot write it in a way that it's analytic, so you cannot really analytically derive Jacobians, you can still use the UKF for propagating mean and uncertainty, which is not the case if you have if you use the extended Kalman filter. An example of a potential observation model could be something like you want to include the uncertainty of an object detector in your observation model. The object detector is an algorithm. It's not clear how you can write this in an analytic form, so you can compute the gradient, but you can still evaluate it point-wise in some way. No? You can just give some points, different inputs to the algorithm. It will give you an output, which is a number, and then you can use it as a sigma points, as a transform sigma points. Okay, so somehow this is another plus of the uncertain transform. They are in the same complexity class. It's just that the multiplicative factor of the UKF is higher, because for the extended Kalman filter you need to have one function computation for the mean, and for the uncertain Kalman filter you need to have 2n plus 1 computation of the function. If the function is very costly, maybe, and the space is very high dimensional, maybe it's too expensive to call this function many times. But as a complexity class, in terms of computational complexity, asymptotic complexity, they are in the same class. And another, let's say this is not plus or minus, they both assume that you are dealing with Gaussian distribution. So they both only consider mean and covariance of your random variable. Okay? If you want to have a look at the literature, there is the Intelligente transform UKF is in the book, Probabilistic Robotics. There is this paper of Julier and Ullmann, which talks about the extension of the Kalman filter for nonlinear system. That's like one of, I think that's where the UKF has been introduced. And there is something else in German, I'm not sure how many of you can actually read it, which also talks about the Intelligente Kalman filter. Okay, so we can make a short break, and then I'll explain you the information filter. So that's the second part of the lecture today. It's about the extended, but in this case, information filter. So before going into the detail, let's see, you remember the Gaussian distribution, no? So we normally parameterize by two values, or two variables, let's say, two parameters. One is the mean, or the mean vector, if you are in a higher dimensional. And the other one is the covariance matrix, okay? That's what's called the moment parameterization. And you then write the Gaussian distribution in this way. There is this normalization term here, and then you have x minus the mean, transpose times covariance, so the inverted of the covariance matrix, and the inverse of the covariance matrix, and x minus mu. Okay, this is not the only way of parameterize a Gaussian distribution, normal distribution. There is another way, which is called canonical or natural parameterization, and it comes from a way of analyzing distributions in class of families. But what matters is that basically you expand these whole terms, and you will get, instead of a quadratic expression in a times sigma minus 1 times a, you will have something which is a quadratic terms like x times variable times x plus a linear term which is x times another parameter plus a constant term. No? So you just expand this. And the other way of parameterizing the Gaussian is by, instead of using these two, is by considering the coefficient of the expanded second order expression. Okay? So they're just a way of rewriting this, and the parameters will just be different, but they will be anyway analytic expression of this other one. Okay? So there's a relation between the two. That's exactly what's called, and we have here information matrix, and we have an information vector. Okay. Now, how are defined? The information matrix is defined as the inverse of the covariance matrix, therefore also the term. The covariance tells you how much uncertain you are, and the information matrix tells you how certain you are about something. And then that's something called information vector, which might be a bit misleading because as per se doesn't tell you too much, but you can see that is the mean vector multiplied by the inverse of the covariance matrix or multiplied by the information matrix. Okay? This comes just because you expand the square, and you will end up that there will be an x transpose xi terms, which is the linear term, and then there is x transpose omega x, which is then the quadratic term, plus some other constant terms outside the square. Okay? How they are related to each other. So we've seen already how the canonical parameters relates to the moment one, and we can just invert these expressions and we get how the moments are related to the canonical one. So to get the covariance matrix, you just invert the information matrix, and to get the mean, you just invert the information matrix and you multiply it by the information vector. Okay? So as you can see, they're just the dual inversion parameterization of the thing. Inversion of the other covariance or information times the other vector, and you get from one to each other. Inverting is kind of costly because you need to invert, so moving is costly because you need to invert matrices, but that's how they are related. So as I said, you can go to the information form by expanding this part. So you just write it down in this way, and you can see that you have a part here, which is the quadratic term, and this is our information matrix. You get the part here, which is the linear term, which is x transpose something, and this product is our information vector. And this part here actually does not depend on x, so you can just ignore in the parameterization. Okay? And that's how we write it down. This goes somehow outside in there. Now this form here, and just as a pointer if you're interested, this is a way of expressing a big family of distributions, which is called the exponential family. They all have similar properties. There is a lot of distributions put there, and sometimes you can reason about them in the same way. So a lot of expressions from statistical theory, they're actually equivalent, where you just substitute the parameters. And they're made in a way that you have normalization, exponential, and then a sum of moments, or actually a sum of sufficient statistics are called. For the Gaussian, you have this and that as sufficient statistics. If, for instance, you get an exponential distribution, it's the same. You only have one sufficient statistics, which is the mean, and basically the distribution look like this. No? You just have the other part. You just have the mean part. You don't have the rest. And then you can build up different statistics. This can be arbitrarily long or short, and can have arbitrary form. But they're all like in the same family. This is just an external point that doesn't belong to the exam, but if you're interested, you can have a look at that. So again, this is the dual of each other's. It's still the same function, you just change the way you parameterize them. But the interesting thing is that operations have different complexity if you do it in one parameterization or in the other. So if you go on, imagine you have this distribution of two variables, alpha and beta, and you can either represent them with the canonical representation here, with eta, which will be the xi. So now the terms are a bit different on the slides. It's taken from a paper of Ryan Eustace. So to not modify and keep the same, but our xi is eta and our omega is now lambda here. And if you express them in this way, you have different forms if you want to do a marginalization. So if you want to take one variable out and getting the integral over that, or if you want to do conditioning, when you can say, which is the distribution of this variable given that I know the values of the other, okay? And as you can see, they are dual in the parameter space. And this is just because one is the inverse of the other, and some operations are the inverse of the other one, and that, therefore you get this duality. So marginalization in the covariance form or the moment form, you just extract the mean of the variable that you care, and you extract the block of the matrix from the variable that you care. Okay? That's because this form here is already in, let's say, a marginal form, in a moment form. So you directly have the moments there. But if you want to do this in the information matrix form, this gets complicated, more complex, more computationally complex, because basically you need to in some way get from the canonical parameterization to the moment one and then do the extraction of the things that you need. And you can do it by just converting and taking the block, or you can exploit properties of matrix inversion to just do it in one way. And that's actually what's done here. We are exploiting the fact that if you do a matrix inversion in here, we can just do an update of this variable here, and we do like a one rank inversion, rank one inversion, and it's just these values minus the inverted of the other variable multiplied by the, let's say, the mutual information in some way multiplied by the variable that you have there. And the same is for the information matrix, or the marginal information matrix. This expression here, again, we have seen something similar on the Kalman filter or on the Gaussian case, but this basically means that the information of a certain variable is equal to the information that you had before minus the information that it shares with the other one. Okay? So that's the uncertainty of the other variable. This transforms this uncertainty back, and then you remove it to the information that you have. Because they are dependent, so when you're throwing one out, you're basically saying, I have less information than I had before. Okay? If they would have been independent, this and this will be 0, so there is no loss of information when you marginalize out. If we do instead on the conditioning case, so where we try to go from one distribution and we take the division, so we remove the completely the information of that and we assume that we know where it is. This is the dual. We need to somehow have an inversion, but on the information space, not on the uncertainty space any longer. And we basically have the same effect that we will have here. But in this case, somehow we need to also remove the mean. So it's beta minus the mean. So we have to put ourselves in a zero mean Gaussian case. And again, for the uncertainty, it's the same. This all comes from the inversion of one rank update. But if we then go on the conditioning case for the information form, everything is easy. We just need to get the information vector of the variables, and we just remove the information vector of the other variable by just multiplying with the common information that they have. And if we want to obtain the conditional information, we just extract it from the matrix. Okay? So you can see already that according to how many operations you need to do with your random variables, one parameterization might be more efficient or better suited than the other one. If you need to do a lot of marginalization, the moment parameterization is actually better. If you need to do a lot of conditioning, the canonical parameterization will be better. Now, when we do filtering, we do both, no? Because we do marginalization from the previous pose, and then we do a conditioning because we consider the observation given the state, no? So ideally, this basically means if I have a lot of measurements that comes very often, but I move not so often, this is better because it's computationally more efficient and it's easier. But if I do a lot of motions and I do not get much observations, then this other one is actually better suited. Okay? So, as you can see, trivial, complicated. Basically, this is just a way of being you aware that you might parameterize distribution differently, and most of the time what you will use is the Kalman filter in many cases because you actually care about the mean, you care about where the state is, but there are cases where it's easier computationally to use the information, the canonical parameterization, get a lot of observation in, update your state, and then convert back to the mean in case you need it. This is just to give you an idea that you can use a different way of parameterizing it. And the idea basically is to exploit the fact that you have different complexities. So according to the task at hand, you might choose one over the other. Next week, we'll see how we can implement SLAM using a version of the information filter, which is called the sparse information filter. And we'll see that you can get more efficient by exploiting some structures in your problem. If you do a Kalman filtering in information form, that's what you call information filter. And you basically have the same step of equations, and you just replace conditioning with marginalizing, so the different equation for the different parameterization. So here is the Kalman filter, again, as we've seen so far. This is the usual prediction step. And now it gets modified by considering the new transformation. So the new information matrix will now be equal to A omega minus 1, A transpose plus R at the minus 1. So it's basically the same as you had before, but you just take the inversion of all the terms. The mean, in this case the information vector, is updated in a very similar way. We have now our expression. We have the expression of the predicted mean, and we can just plug it in, and we obtain that our information vector is omega times inverse A times the converted mean plus B plus UT. Okay, so you always have this kind of conversion when you do the update, and that's somehow an expensive part because you have matrix inversion there, unless this matrix has a special structure that can make it efficient. Okay. So this is how we modify the prediction step. And now we need to modify the correction step. So we can, this is how we normally do in the base filter. So we have this observation model, we have the predicted belief. If you expand it from the Gaussian case, we obtain this expression here. So we have here the expression with respect to the likelihood, and here is the expression with respect to our predicted belief. If we keep on expanding and putting everything together, we can then collect few terms, and we will end up, I mean, I'm just skipping a few of this, but that's how, just believe me. You can open up, collect terms that have that correspond to the same variable. So you collect the quadratic term all together here, the linear terms all together here, and we will have the new information vector, which has this particular form. It's the C, which is our observation matrix, multiplied by Q minus 1, which this was the covariance matrix of our observation model, and now since it's inverted, it's the information matrix of our observation model. We have the usual transformation. Now, since we are in information space, we are actually using C transpose QC instead of putting the transpose on the other side, and plus our previous information matrix there. Okay, this is the new information matrix, and for the new information vector we have something similar. We take the previous information vector, we take our observation matrix, and we take the information matrix of the observation times observation. So as you can see from here, the interesting part is that this is now very easy to do the update, because for doing a measurement update, we just need to get the measurement information vector, information matrix, propagated through our observation matrix and add to our information matrix. So the more information, the more observation we get each time, we just need to sum them up. So it's really just summing all these values up, and the same is for the information vector. Okay? And in case you have very sparse observations, this is just a matter of summing few numbers. Okay? And that's where, let's say, the information filter is useful. If you have a lot of observations and not much of motion, so not much of prediction. Basically, if you don't care about marginalizing out the mean, you just care about getting the full trajectory with all the observation in, you never use this prediction step where you need to marginalize over the previous pose. You just only have observation in there that you sum them up. Okay? And you'll see that this somehow gets the same intuition when we will go on optimization-based or graph-based LAM towards the end of the class, because the idea is the same. It's just going on the other space and tries to see if you can exploit some of the structures there. So if we go back to the information filter algorithm, now we can also include the prediction step. We know how to compute the new information matrix. We know how to compute the new information vector, and we can just return them. So these are the two steps, and there are some main differences. I don't know if you want to point them out, but do you see them? Which is one of the main problem, so not problem, but like which is one of the, besides the duality thing, there is another part of the information filter which might be not as useful as it might seem at the first glance. So imagine that I'm trying to do localization, so I want to know where I am. How do I know where I am using this? So when we use the Kalman filter or the moment form, we know that the mean represents where we are, right?
You would have to do the transformation back to
Exactly. So in case you need to know where you are at every time step and very frequently, this means that you have to often do an inversion of this guy here, multiplied by this guy, and then you can get where you are. Now, you can keep track of the mean over time, so you can actually have an over-parameterized system where you keep the information vector and the mean on the side, and then you always reuse just few updates of the mean to quickly get something, or you can do some other tricks. But in principle, recovering the mean is a bit more complicated, so it might require a matrix inversion, or might require solving a linear system, or something like that. So that's one of the problems, and the rest is just if you need to do more often marginalization, it's complex for the information filter, but it's easy for the Kalman filter. If you need to do more often corrections, it gets easier for the information filter, it's harder for the Kalman filter. In terms of complexity, here you can see the specular thing. You have 2.4 complexity for the prediction step in the information filter against n squared complexity for the Kalman filter, and the other way around for the correction step. Now there is also a bit of slight difference. The Kalman filter has a costly correction step, but in the dimension of the observation space, while the information filter has a costly prediction step in the dimension of the state space. So if you have very sparse observation, this is still quite efficient. But if you have the dimension of the observation is similar to the one of the states, like if you're doing localization, for instance, or if you're doing SLAM, but you observe a lot of landmarks at the same time, so you get in the same kind of class of complexity, then they're roughly equivalent. There is one interesting aspect in SLAM, is that if you consider the information filter, you have very sparse information matrix, because you have only normally pairwise measurements, which is connecting one landmark with one pose or few landmarks together. But if you then invert this matrix, you can then get a dense covariance matrix. And there are some tools that exploit sparsity in matrix for having efficiency in operation. So many of the operations here and also in the prediction step, if you have a sparse matrix, you can have them in linear time, where n is the number of the non-zero elements in the matrix. Okay, so and we'll see next week how this is actually done. Again, when we have nonlinear models, we need to get the extended information filter, and we do the same tricks. We can do the same tricks as the extended Kalman filter. In principle, one could do the same trick of the unsending Kalman filter to have an unsending information filter, and so on. One problem here is that we need to have a mean for doing the linearization, so we still need to somehow extract the mean from the information filter, okay? Which pose some limitations in case you have very high dimensional space, because you need to invert the information matrix. So we get now from the formula of the extended Kalman filter, we can get back again to the extended information filter, but here, since we need the mean to do the linearization, we need to extract the mean in this part. And the update of the information matrix is the same as the linear case, where we replace the function g with the Jacobian capital G. Okay? The rest is basically the same as we've seen for the linear case. This again gets modified from this part, which is the extended Kalman filter, to the new updates of the extended information filter, where we have the mean recovery and mean computation as an additional step. Okay? Because we linearize around the mean every time. The correction step is again similar. We need to recover the mean, but we can also expand the state by just considering the mean that we computed before and propagating through the function. So we don't need to compute it again and again. And we can end up to the final form of the extended information filter, where we have this part here, up to here, that covers the prediction step, where we recover the mean and predict the mean. And then we have this part here, which is the update step, where we get the Jacobian of h with respect to the mean, the predicted mean, and the function computed mu with respect to the predicted mean. If we want to compare the two, they're basically doing the same thing. They are just different way of parametrizing the distributions which are behind. So they have the same power, and they have eventually the same complexity, but it depends on the task which one can be more efficient or less efficient. And in generally, it is been shown that might be more stable than the extended Kalman filter in terms of numerical stability. So, and there's just it's just an empirical found. There is not much of a theoretical understanding down there. But in practice, the AKF is more popular, is used more often, and that's also because you don't have to always get back to recover the mean, and most of the time what you actually care in filtering is know where your system is, and this means knowing where the mean of your distribution is. But again, if you look at different angles and you have different frequency of operations, recovering the mean might be more computationally feasible than doing the full Kalman filter all the time. Okay? So in summary, the important thing of today is that we can represent Gaussians in a different way, and if we represent them in this canonical form, we can also re-express the filter that we've seen last week, the Kalman filter, in terms of this new parameterization. And we have seen that for the Kalman filter, we have an efficient prediction but slow correction step, while for the information filter, we have a slow prediction but an efficient correction step. Again, at the end, it depends on which is your application. It depends what you care more. If it's more prediction or more correction, you might choose one for another. Okay? So that's it for today. There is a chapter on extended information filter in the book. It's chapter 3.5. You have a look at them. And if you have any questions now, we still have a few minutes left. Just ask. No? Okay, so then that's it for today. Let's see you next week.